Hey everyone, thanks for joining me again. In this video what we're going to do is we're going to use a little bit of programming to experimentally verify a theoretical result from probability. In particular, we're going to look at the probability of having exactly one pair in your hand if you're dealt a 5-card poker hand. And if you're not familiar with poker at all, I think you'll still find this example fairly intuitive, easy to understand. We're going to use Python in this example, so if you're not familiar with Python, then I hope you'll at least be able to follow along with the way that we create our functions and our algorithms. And also know that I'm not an expert in Python, so if you are familiar with Python and you see me doing something that's not Pythonic, as they say, first I hope you'll forgive me, and then also if you want to give me some advice or some suggestions about how to make my code a little bit more efficient, please feel free to do so in the comments below the video. Alright, so for this problem, a couple of days ago, I created a blog post, and it just goes over how to calculate the theoretical probability of having exactly one pair in your hand being dealt a 5-card poker hand. And now, understand that I'm saying you have exactly one pair, not at least one pair, but exactly only one pair. And if you do the calculation, and I'll put a link to this blog post in the description below the video if you want to follow along with the calculation, but when all is said and done, you end up with the result that you have about a 42% chance of having exactly one pair in your hand if you're dealt a 5-card poker hand. All right, and this is a well-established value. It's been around, I'm sure, for hundreds of years, so there's nothing original here. But today, at least for exploratory purposes, we're going to use a little bit of programming to set up an experiment and verify that this value follows our intuition, and I'm sure that you'll be convinced that it does by the end of this example today. Alright, so you can use whatever Python environment you like. I'm using a Jupyter Notebook here. Alright, so and I've already gone ahead, imported the necessary module, which would be the random module, and also I've created a deck of cards, or I've set up the code to programmatically create a deck of cards. Now, I'm assuming that most people are familiar with a deck of playing cards. You know that there are 52 cards in total. That means that you have 4 suits: clubs, hearts, spades, and diamonds. And then for each suit you have 13 different ranks, ace through king. Right, so that's 13 times 4, that equals 52. And you can see I've just used a little double for loop here to append to our deck list a bunch of tuples, and each tuple represents a card, its rank, and its suit. So if we print out the deck, you can see that we have a deck and it's perfectly ordered. We have 4 aces, 1 for each suit. We do that all the way down through kings. We have 4 kings, 1 for each suit. So we've got a good deck here. Now what we need to do is shuffle the deck. So we can create a function called, and we'll just call it shuffle deck. It doesn't take any parameters. Alright, so first we're going to use our deck that we created in the previous cell. So we don't want to mutate it at all, so let's create a copy. Alright, so we'll say deck copy, and we'll use the copy function to get it. Also, we'll have to set up a list that we're going to take random cards that we draw from our deck copy, and we're going to put those cards into the list, right? And they'll be distributed throughout the list randomly rather than in ordered fashion as you see up here. So let's just call that shuffled deck. And then what we're going to do is we want to do this 52 times, which would be the length of our original deck, right? But every time that we take a card from it and we put it in our shuffled deck list, we're going to have to remove it from the deck copy list, right? Otherwise we'll end up with 2 of the same card. And if you do that in a casino, as you well know, you're likely to be taken off to some back room and dealt with in a most unpleasant manner. So rather than have that risk be with us, we'll go ahead and get rid of that. And we want to do this we want to do the drawing of the card, or the getting the random card for our shuffled deck list 52 times, so we can just use the length of the deck list. All right, so we can say for I in range, and we'll use the length of deck, not deck copy, because that length is going to be reduced every time we remove a card. So what we want to do is grab a random card, and we'll just call it random card. We use the choice method from the random module and choose from deck copy. Alright, and then we want to add that to our shuffled deck list. And then we can't forget to remove it from the deck copy list. And then we'll want to return our shuffled deck. And let's go ahead and just print out a copy of it so we can see what it looks like. Alright, so, as to where before we had a nice ordered deck, this one looks fairly disordered, right? It looks fairly random. If you want to increase the randomness of the deck, I guess you could have it do the shuffling 3 times. I mean, if you're in a casino, they never just shuffle it once, so. But for this example, we'll just go ahead with one single shuffle of the deck. Alright, so now that we have a shuffled deck, we'll need to have a function that deals out 5 cards. We're not playing Texas Hold'em here. You could have a function that deals out 2 cards. Right, what we'll do is we'll create a function that takes as a parameter the number of cards to be dealt. So again, with Texas Hold'em it would be 2. But we're playing 5-card draw, so we're going to have it just deal out 5 cards to each player. So we'll call this function deal n cards, and it takes as a parameter the number of cards to deal to a player. Alright, so what we'll want to do is we'll want to have an empty list that we can push or append values to, and those will be the cards that we draw. Alright, so let's just call this list drawn cards. And actually, we'll want that to be an empty list. And then we'll loop over. We're going to do a for loop, but we're only going to draw 5 cards, right? So, or as many cards as are in, as this parameter here represents. So in our case, it'll be 5 cards. So what we'll do is we'll say for I in range num cards. And you probably already caught it. One thing I forgot to do is actually get a deck of cards, right? And it needs to be a shuffled deck. Right, so first what we'll do is we'll bring that in. Okay, now we have a shuffled deck of cards to choose cards from. All right, so it's random.choice shuffled deck. Okay, and we want to add that drawn card to our hand, which is drawn cards. And then we'll want to remove the card that we put in our hand from the shuffled deck. If you're following along, be careful you don't do what I just did and confuse drawn card with drawn cards. Drawn cards is a list, and drawn card is a single tuple that will be added to the drawn cards list. And then we'll want to return drawn cards. And let's check and see if we get a 5-card hand that has no duplicates. Let's call it my cards. Alright, good. So we have a 5-card hand right here. In this case, we have no pairs. Alright, and if our theoretical probability were very high, like say 80 to 90%, we'd be concerned that we didn't see a pair already. Alright, but we'll see one soon enough. If we run it again, alright, again we see no pairs, but again our theoretical probability is less than 50%, so that's not too surprising. Alright, so now we see a pair. There's a 4 and there's a 4. And we see only one pair, we don't see 2 pairs. Run it one more time. Sorry about that, I ran the wrong cell. Okay, and we see no pairs here. So we did it, what, 4 times? We saw 1 pair out of 4 tries, so that's 25%. So it doesn't quite match up with our theoretical result, but we're going to have to do this a number of times, a large number of times, to get close to that result. Right? Remember, it isn't just a few times that you can do this. It's doing a large number of trials, repeating the same process over and over and over again, and seeing that eventually you end up with that theoretical probability. And you'll see that as we go on. Alright, so now what we'll do is we'll create a function that allows us to check whether or not we have a pair, because we're going to do a large number of trials. We're not going to keep doing it by hand as we just did right now. So in that sense, we need to have a function that automatically checks whether or not you have exactly 1 pair in your hand and then moves on. It gives you a true or false value. So we'll call that function check 1 pair. Right. Now this is going to take as its input a hand, a poker hand, right? It's going to have 5 cards. This is a poker hand right here. Alright, so what we'll want to do is, for each card in the poker hand, we'll want to just get the rank, right? So you have here a tuple, and for each card you have a tuple, and the first value of each tuple is the rank. Alright, so we can get the ranks. We'll use a list comprehension here. And we'll get the first element of each tuple. Let's just make sure that we're returning, or we're getting those ranks. All right, so we'll return ranks for now. All right, now we can't just pass hand in, we have to get that hand, right? And we get that from DLN cards, passing in a value of 5 for our case. Good, so we've got a list of ranks. There are no suits here, and that's good. All right, if we run it again, still no pair, that's 2 times. Run it again, still no pair, that's 3 times. Run it again, and finally we get a pair. So actually we are at the same, we're getting the same result as we got the first time around, right? 1 out of 4. Right, but again, that's not the theoretical probability, so we're going to have to do a large number of trials. Well, we're going to do a large number of trials regardless. That doesn't really, it's not making us do it. We're doing it because we don't want to just do a few numbers and trust that we're getting the right results. And of course, you don't want to keep doing it just so that you can make sure it matches up with the theoretical result as well. Right? At some point, you're going to have to figure out if your experiment is bad or if maybe you've misunderstood the theoretical result in general. All right, so going back here, let's finish up our check 1 pair. Function. All right, so we'll want to use a dictionary to keep track of how many values of each rank we have in our hand. So let's call this value counts. All right, and we'll just set up an empty dictionary. Okay, and then what we'll want to do is go through all of the ranks that we have and assign a value count to our ranks list. And that's for each rank. Right, so we'll loop over that ranks list. All right, and then we'll compare what we see to our value counts dictionary, right? So for example, if we look at the rank and we see that it doesn't exist in the list of keys in value counts, then we'll go ahead and add it to it, with a value of 1. That'll be the first time we've added that rank. All right, so again, when you have a dictionary, you can get all of the keys of the dictionary just by using the keys method, right? And that'll be a list. All right, so we can say if value counts dot keys, right, which is the list of keys, and we'll say if rank if the rank is not in that list, right, then we'll want to add it to value counts for the first time. Right, and that'll be equal to 1, right, because you do have 1 count now that you've added it. Now, the else case means that actually you already have 1 of that rank in your ranks list, right? Or sorry, in your value counts dot keys list, right? And if you do, then you want to add 1 more. Right, so we'll add 1 more that way. All right, so now we have this value counts dictionary. And actually, let's take a look and see what that looks like real quick. So let's return value counts. Okay, so that you can see here we've got 1 ace, 1 3, 1 jack, 1 10, 1 8. All right, so there are no pairs there. Let's run it again. Okay, now you can see we've got 2 pairs, right? We've got 2 queens, 2 4s, and 1 10. Right? So this is still not a successful result, right? Because we only want to have exactly 1 pair. So I'm glad we saw this. Let's do it again. All right, again we see no single pairs. Finally, we've got a case where we have a single pair, right? That's 2 jacks. All right, so that's what value counts looks like. So we want to check to see that for all of these values, right? If you look at all of the value counts, all of these, 1, 1, 1, 1. If you want to see that the number of 2s, right, the number of values that equal 2, you want that to equal 1. You don't want it to equal 2, right? You don't want it to equal 3, which it can't anyway. I mean, you're not getting 6 cards, right? We only want to check to see that the value of 2 occurs 1 time in our value counts dictionary. And if we can verify that, then we know we have a pair, all right? And then we can return that as a value of true. So what we'll do is we'll return. So what we'll do is we'll look at the value counts values, not the keys, but the values. Right? So value counts dot values. All right, and then we want to use the count method. All right, and we want to count the number of 2s, right? The 2s in our value counts dictionary. Right. Here we have 1, 2. And we're returning it when that value equals 1, right? When we have exactly 1, 2. One value of 2 in our dictionary. Okay, and that will return true if we do, and it will return false if we don't. All right, so let's see what happens here. And I can tell you ahead of time you're going to get an error, and you might have already figured this out if you are very good at Python. And by the way, yeah, let's go ahead and do that. So it says here, dict values object has no attribute count. So what we need to do is we need to make it a list, right? So we'll use list here, and that should be good. And a friend of mine showed me this just today when we were talking about it. All right, good. So you see that it's true. That means for this iteration we did have a pair. If we try it again, we'll probably see false, and we do. All right, we're likely to see false because we're not likely to have a pair that often. Okay, so for each time that we check a pair, we just get either a true or false value, right? But we don't want to do it only one time. We want to do it a bunch of times. All right, so we want to see how many times we get a true value, right, which would be equal to 1, or a false value, which would be equal to 2. Sorry, equal to 0, excuse me. All right, so what we can do is we can define a list called successes, right? How many times we actually have a pair, right, which will be represented by a true value. And this can be a list comprehension. All right, so like we did before, we can use the check one pair function. Pass into it deal n cards. All right, and that'll be 5 cards. And let's just do it 100 times for now. All right, we'll do 100 trials. All right, so if you just want to see what this list looks like, we can print that out. All All right, so you've got a list that should have a length of 100, right? It has some true, some false values. We could go through this and we could count up the number of true values and then divide it by the total number of values, which would be 100, and see if we're anywhere near our theoretical probability, right? But we don't want to do that. That's tedious, so we'll just do it by using the sum function, right? So we can say sum of all of this, and actually let's not do it here, let's do it below just for readability. Right, and you can sum this list. I know it has true and false values, but Python will consider them as equal to either 1 or 0, and again, that's something that a friend of mine pointed out to me today. So what we can do is we can say probability, and let's say experimental probability. Let's call it experimental probability. That would equal the sum of that list, right? Successes, right? But then we want to divide it, right, by the total number of trials that we're doing here, right? Now in this case, it's going to be 100, right? Because our list is going to be length 100, right? If we want to, we should create a variable that makes it easier, right? We'll call it num trials, and then we'll just set it equal to 100 here. You also could have just gotten the length of the successes list, right? And that probably was the easier way to go. All right, so let's see what we get. Would help if I actually told Python to print this out for us. All right, it's 53. Do it again. 0.4, that's a lot closer. 0.41, that's getting even closer. 0.45. 0.41. Recall that our theoretical value was 0.4225, right? So we're doing all right here, but 100 trials is not really that much. We could do 1,000 trials and see what it looks like. All right, so we're consistently close. All right, and if we bumped it up to, let's just do 10,000 trials, see if we stay pretty close each time. That's close. That's close. That's close. That's close. So we can set a tolerance, right? We can find out if we're within an acceptable error range, right? So we could say that and that was again. All right, let's go there. And then let's print out. All right, so that's a very small number. So the difference between experimental and theoretical is quite small. All right, so what? 6/10,000ths here. 7/10,000ths about. So if we bump this up to 100,000 trials, we should get an even smaller difference. Of course, it takes a while to run because this is a larger number of trials. All right, so that actually was worse. Let's try it one more time. Seems like we're doing worse with a larger number of trials. All right, so I guess we got kind of lucky with the one we had, what, 10,000 trials, and we ended up with a really small difference. But I think we got really lucky there. We just got really close to the theoretical probability. But for the most part, it looks like we're off. It looks like we've got a difference of 1/1000th. Try it a couple more times. All right, there's 1/10,000th. And there's 1/1000th again. All right, so it looks like maybe with 100,000 trials, we're getting, an error of about 1 in 10,000, or sorry, 1 in 1,000. Right, and we can take an average of the errors as well, right? So we can say let's not call it error, let's just call it difference. We'll do it. If we do it 100 times, it's going to take a while. Let's do it 10 times. And we'll take a look at that. All right, so not only are we taking the sum, of course, we want to see the average. So we want to divide it by, and we're doing it 10 times, so let's just go 10. Let's see what happens. What do we do wrong here? It's easy enough to fix. All right, it's going to take a little bit of time. Oh, there it is. Okay, so there's 2 1,000ths. All right, let's try it one more time. This will take a while, but let's try it anyway. And yeah, I completely understand if you're bored at this point and you've got it and you're ready to click off this video, but I like being thorough about these things and really feeling confident about my results. That's why I'm doing it again. Okay, so somewhere between 1 1,000th and 4 1,000ths or 4,000ths, and let's just do it again. glutton for punishment. Alright, so probably the most common value we've seen is about 1/1000th. So anyway, that gives us an idea that we were able to calculate or show, not calculate, but come up with that a value close to our theoretical probability through experimentation. And, you know, we can't guarantee that we've set everything up perfect, or at least I'm not willing to say for sure that we have, but I feel confident that our experiment has been meaningful. So, you know, if you have some suggestions as how to tweak this experiment and do a little bit better, be a little bit more accurate, and of course, if you have any ideas about how to make the code more Pythonic, please let me know in the comments below the video. And with that, I'll see you next time. Cheers.